9, section 5.2, the addition rule complements video 3. In the previous video, we saw a contingency table and calculated some probabilities. I've summarized them here, but I'm going to use two capital letters to represent the events that we looked at. A is the event that a person was likely to vote, and B was the event that a person favored the bill or the proposition that was being voted upon. And in the previous example, we calculated the following probabilities. The probability that somebody was likely to vote was 721 out of 1,000. The probability somebody favored the proposition was 523 out of 1,000. The probability somebody was likely to vote or they favored the proposition was 872 out of 1,000, and the probability that somebody was likely to vote and favored the proposition was 372 out of 1,000. Now, why did I extract this and represent the events with single letters? Because I can? No, because I want to see if we can find a relationship between these four probabilities. Recall that when we calculated the probability for the OR compound event, we circled one row, one column, but we couldn't just add their totals. Why not? Because there was somebody that counted twice in that total. The people who were both likely to vote and favored the proposition. So if we wanted to find the probability of A or B, we can't just add their probabilities. Because if we were to just do that, the people that were in the first row would get counted twice when we also counted the people in the first column. So the people in the intersection were counted twice. But what do we know about the people that were in that intersection? When we circle the first row and the first column, what do we know about the people in the intersection? Well, those were the people that were likely to vote and favor the proposition. That got counted twice, so to balance it out, we should subtract it once. And in terms of probability, that means we would have to subtract the probability of A and B. I know when we added them, we weren't calculating probabilities yet because they weren't on top of 1,000. So think of this just as counting how many were in rows and columns as opposed to putting them over 1,000 and making a probability out of it. The number of people that were in the first row or the first column is the number of people that were in the first row plus the number of the people that were in the first column. But the ones in the intersection were counted twice, so we have to subtract the number of people that were in the first row and the first column simultaneously. This is called the addition rule. And it's a rule that allows you to calculate the probability of an OR compound event if you know the probabilities of the individual events and the probability of them happening simultaneously. For example, let's say that the probability that you draw an ace is, we'll keep it out of 52. 4 out of 52, because 4 cards out of 52 are aces. The probability that you draw a diamond, there are 13 diamonds out of 52. And yes, that can be reduced, but let's leave it with the common denominator. But you also know that the probability that a card is an ace and a diamond, out of the 52 cards in the deck, how many of them are the ace of diamonds? One of them. So we know all of those probabilities. 4 out of 52 chance of drawing an ace, 13 out of 52 chance of drawing a diamond, only 1 out of 52 chance of drawing a card that is both an ace and a diamond. We could calculate, or I could ask you to find, the probability that you draw an ace or a diamond. For example, you're playing Texas Hold'em, and you have an ace king of diamonds, and somebody is ahead of you, and you've got one card to come. They've got a pair of kings. You can win if you hit an ace, or you can win if you hit a diamond. Now I realize in that scenario you have to remove the cards that you're already holding, but that's just an example of an OR probability. To find the probability of an OR compound event, all you have to do is use the formula. The probability of an OR event is the probability of the first event plus the probability of the second event minus their joint probability. Probability of ace and diamond. I realize I just used a vocabulary term out of habit, but a joint probability is a probability of two things happening at the same time, jointly. Well, I know all of these. I know all of these probabilities. The probability I draw an ace is 4 out of 52. Plus, the probability I draw a diamond is 13 out of 52. Now, why can't I just add those? Because somebody got counted twice. When I count the aces and I count the diamonds, which card got counted twice? The ace of diamonds. And that's what this minus is about. There's only one card that is both an ace and a diamond out of the 52. It got counted here, and it got counted here, and we can't count it twice. These all have a common denominator. 4 plus 13 is 17, minus 1 is 16. And that's the probability of drawing an ace or a diamond. We could check this really easily. Let's count all the diamonds. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King. There's 13 diamonds. Now let's count the rest of the aces. Remember, I already counted the ace of diamonds down here. So 13 plus the other 3 aces, ace of clubs, ace of spades, ace of hearts. 13 plus 3 is 16. So the answer does check out. So the addition rule again, the probability of A or B equals the probability of A plus the probability of B minus the joint probability of A and B. This is a formula I would give you on your formula chart.